Hello, Count Sacke here, back with another Genshin Science peer review video. Today, I will be covering What If Dragonspine Existed in Real Life by Bata325. For those who are wondering, Genshin Science peer review is a series dedicated to looking at various social media posts about Genshin and science. I take a look at their work and then analyze and critique it. That is the main goal of peer review after all, to improve and get closer to the truth, essentially. If that sounds interesting to you, I also have various other Genshin Science peer review videos as shown here, and I have currently 3 other videos. In fact, this video is actually meant to have 2 parts, so if you don't want to miss out on part 2, be sure to subscribe. While you're at it, you can also become a channel member where you can gain access to various perks, such as being able to view videos early without mid-roll ads. Anyway, you can also like, share, and comment down below, or even leave a super thanks. With that, let's get back to the main video. So, what exactly is this video about? Well, the main goal that it has in mind is to essentially calculate the height of Dragonspine and then make some various scientific, or make some various conclusions about it. Now, that is not all of that the video is about. In fact, if I go to the video here, that is more or less about 6 minutes worth of the video is dedicated to math and physics. And that is the only part that I will be covering. Well, actually, I'm only going to be covering an even smaller bit of it, and because a lot of the early part is more of Bata explaining the process and how he developed the methodology for the experiment. And he does it in a pretty quick way too. And, well, if you haven't seen the video, please do watch it. I found the video very entertaining to watch, and this is actually, and by the way, this is part of my peer review, being able to convey ideas and whatnot. In terms of presentation, it was very fun and enjoyable to watch, which makes it all the more worth it. I actually found it quite funny as well, because I was actually laughed a few times throughout the video. It's a pretty short video, it's only 10 minutes long, so I do really highly recommend that you watch it first before continuing on with this video. With that out of the way, let me go ahead and continue. Another praise that I have for Bata right off the bat is that the video does a really good job at explaining the various concepts very quickly as well. Like I said, 6 minutes of this is mainly dedicated to the math and physics portion of it, and within that portion, I was able to understand what exactly was happening for the most part. That's my praise. In science communication, being able to explain ideas is very important. If nobody can understand what you're doing, then it's kind of pointless, because nobody can even check if you're right in the first place. So yeah, great job on that. So, there are 2 main different parts to Bata's video. First is that he actually measures the gravitational acceleration of Teyvat. And in the second part of the math and physics portion, this is where he actually measures the height of Dragonspine. So again, just to point out, our first part of our video will only focus on this part where they measured the gravity. And in the second part, I'll talk about measuring the height itself. It's also worth noting that when Bata is saying height, he doesn't mean its altitude or elevation, which if you consider a mountain, you typically measure it from sea level. So if a mountain is like this and the sea level is down here, so that's the sea level, and then there's like some ground or something, and this is the top of the mountain. You can have an altitude like this, but Bata wants to consider this height, this smaller height, h, rather than the altitude over here, which I'm labeling a. So yeah, that is what Bata means by height of Dragonspine, from the base of the mountain to the very peak of it. So again, let's now talk about how Bata measured gravity. So, what exactly did he do? Well, to measure gravity, the very first thing he did is to make use of the kinematic equations. You can measure our gravitational acceleration with this equation. Delta y is equal to gt squared divided by 2. Now, you can actually simply solve for g, and then you'll have an equation for measuring the gravitational acceleration of Teyvat. In fact, this is the same exact method that I used to measure the gravitational acceleration in my first video about gravity. So, yeah, if you're more interested in where this comes from, I would recommend you watch my video about gravity. So, from this equation alone, we can actually see that there are two different values that we need. We need to measure the height, and we need to measure a time. So, how exactly do we measure the height? Well, put very simply, what Bata did was he used the quest tracker. But exactly how did he use it? Because it's also important to figure out the setup for this, because the quest tracker will simply tell you the diagonal distance from, well, the marker to the player. So it has to be a bit more, we have to be a bit more specific on what's happening here. So let's say that we have some sort of ledge over here, and then we have the ground, some lower ground here. And then we have our quest marker right there. If we station or position the player right directly above this quest marker, then we would be able to measure the distance from this marker to the player, which just so happens to also be the height. So as you can see here, it will simply just be this distance here. This will be shown on the quest tracker, and it will be h. Now, this is where I have to say that there is a bit more to this setup than that, because how exactly are you going to position your player above a marker when they're not even standing on anything? This is where I have to give some more praise to Bata, and it is the fact that this is not just any character. This is actually Zhongli. And if you know anything about Zhongli and his capabilities, one of the things that he can do is to summon a pillar. So basically, Bata will create a pillar on the side of some sort of ledge where there's a quest marker directly below, and position Zhongli above that marker. And with that, he's now able to measure the height with the quest tracker. And what's even more genius about this setup is that once the pillar disappears, Zhongli will be able to, well, fall, and you can measure the time. So essentially, you have this setup that's all in one, and you don't need to change anything. I cannot stress how cool this setup is, in my opinion, because back in my first video, I'll just show it on screen, I actually had a very different setup for how I would be able to measure a height with just the quest tracker. And what I actually did was I had to find a ledge where it was possible to stand in directly below it. So if the player could stand up here and stand down here, and the quest marker was like right over here or something, you could use Pythagorean theorem to actually measure the height. So that is actually how I had to do it, but this involves me having to go up here, measuring the diagonal distance, then going down here and measuring this distance. And yeah, this one is all in one. You don't even need to do this extra bit of work. So that's how he measures height. And I briefly talked about how he measured time, but there's a bit more nuance to time. And unfortunately, this is where my most negative critique about Bata's video comes in. When he measured time, he actually specifically expressed that he had a little bit of difficulty in doing that. Because, well, there are times where he struggled to figure out which is the very first frame the player starts to fall. So, is it this frame or is it this frame? Honestly, looking at this, I can't tell. Even though I've done a lot of this stuff where I go in frame by frame, look at the characters and see things, I personally cannot tell, because I do feel like I do need more than just these two frames to tell if the player is falling. Let me just explain what Bata does. So, first of all, I think it's important to just write down there is confusion about when to start measuring time. So yeah, that's the main problem. We don't know when to start and we don't know when to end. Well, mainly Bata only mentions start, but I might as well mention end as well. Well, what Bata does, and well, let me go ahead and try to illustrate this. So we'll have like maybe we have sample 1, in which Bata measures a time, and then that time will be used to calculate a gravitational acceleration. Then on sample 2, let's say that we have the problem where we can't tell which one is the start, or which one is the starting frame. So we have T1 and we also have T2. What Bata does is Bata calculates the gravitational acceleration for both of these. So he has one for T1 and one for T2. With these calculated values of G, he compares them with the previous other sample calculated values for G and selects T based on if it matches the other values of G. This is not good. This way of choosing your sample data or measure is not a good thing, because this is very prone, and in fact is prone to bias. Another thing to note is that it makes your data dependent. Your sample data is now dependent on other samples, so there is no independence. And that's actually kind of an important thing in statistics. Your samples ideally should be independent from each other, meaning that they don't influence each other, or it depends on your experiment. Sometimes you might want them to, but in this case, we don't want our samples to depend on each other. We want them to each be individual samples or measured times, and we don't want one time to influence the other. Otherwise, we get bias. So it's important to say here that just because the data is biased doesn't necessarily mean that the value that Bata calculates is wrong. It's just saying that whatever value of G is, it is leaning towards a specific value, and it may or may not even be correct. So whatever this value is, we just hope that it's not the wrong value. This would not be too big of a problem if your sample count is particularly large. With a larger sample size, it will minimize the effects of this bias, so long as most of the samples do not have this problem where there are multiple times that he needs to consider. Unfortunately, you can actually see that he only has 4 samples. I do have to say that your data is very likely biased, which is not a very good thing. Here's a piece of advice I just want to give to Bata right now. Let the data speak for itself. So data should speak for itself. What this basically means is, well, we should not have our own, I should not be using the other previous sample data to try to infer what the next sample should say if we want them to be independent. So how exactly do I personally accomplish this? Because this is a problem that I also sometimes face when doing measurements in Genshin Impact. Sometimes it's hard to tell when is frame 1. What I personally do is to use the character animations as reference. In Genshin Impact, or in the case of our setup here, where we have Zhongli standing on top of his pillar, and then eventually the pillar disappears and then he falls, there are a total of 3 different animations considered. First is a standing animation. Typically this would be their normal breathing, that you can see their shoulders and arms slightly swaying. And then second is a falling animation. typically what happens in the falling animation is that the player's arms will start to race to the side. And well, yeah, and the third one is a landing animation. Now, technically speaking, I would say that the falling animation is more of split up into two parts. First one is a transition, and the second one would actually be a looping animation where the player just kind of continues to, where they continuously fall. But for our case, let's just consider it to be these three. So when the player is standing, you know, they typically might look something like this. They might have their arms on the side, but when they begin to fall, you'll notice that their arms might actually go up a bit like this. Now, I'm kind of exaggerating here, but yeah, you get the point. And then, of course, on the landing, you'll actually see that maybe it looks something like this. I don't know, forgive my awful drawing. But yeah, as you can see, there are clear differences between each animation, and being able to use these really does help to actually show how the player's state is. When the player is standing, well, obviously he's on the ground. And well, yeah, in code, you have to literally update the player animation alongside the player's position and whatnot and how they're moving. If we know that the player is falling, or if we can see the player animation update or transition from the standing to the falling animation, we can tell that they are now actually falling. And that is how we can mark when the player begins to fall. And that's how we figure out our start time. And if we want to know the end time, we look for the animation for when the player snaps to this landing animation. And now, I guess to demonstrate this, I will go ahead and open up DaVinci Resolve, because I actually have video clips back from this very first video still on my laptop right now, so that's actually quite a fun coincidence, so I might as well show it to you. Alright, so here I am in DaVinci Resolve. I'll go ahead and drag in my clip here and put it down into the timeline so that way you can see. Now, I'm actually using DaVinci Resolve for a very important reason, because it actually does genuinely help to have it. So essentially, I would have a situation where I would position Aether on top of a floating platform. If only it would actually update and show. Please do. So, and inside, I would eventually move the platform so that when I actually go to exit out of the edit mode here, so you'll see that I'll exit, the player begins to immediately fall. So that is basically the setup for how I did this. Now, let me go ahead and actually show how I measured the time here. So let's start off with this very first sample here. So you can see here, well, how exactly do I know when to start? This one is even a little bit more tricky because the screen is completely black. So we don't even know exactly when does the player start. So first of all, I'm going to clean up my timeline so that way we don't have any problems. And I'm also just going to make some other cuts. Hopefully the player has landed by then. Yeah, they have. Okay. Now, let's start off with the end time because that one is more easy to tell. So let's find the very first frame. And yeah, this is what I mean by you can see that the player is in this looping animation. So right now you can see the player is currently in a falling animation. It's just looping. They maintain this exact position for their arms and legs. But the moment that Aether hits the ground, you will immediately see a change in how their arms and legs are positioned. So when the player hits the ground, right there, you can see that one of his legs is on the ground, his leg is forward, and his arms have changed. So you can see that there is a clear snap to a different animation state. And yeah, very much, it changes to this landing animation. So personally, I always do it on the first frame that we see the change. So this is the first frame I saw the change, so I'm going to make a cut here and delete the rest of it because I don't need it. But what about the start? Well, it's actually a little bit difficult to tell, but if you actually zoom in really close here and go frame by frame, you can actually see here that you can just barely see, but there is a little bit, you can actually see the player right now. Now, it's hard to see because, well, you know, because it's very dark. But the reason why I'm saying DaVinci Resolve is particularly helpful in this case is because, well, DaVinci Resolve has this pretty amazing color thing, and all I gotta do is to change the gamma. So what I'm going to do is just increase the gamma by a lot. And nothing is happening. Oh well. Great job. Oh, there we go. So yeah, you can see here now that the gamma has increased, you can now clearly see the player. So there's just this one frame where we immediately see brightness, where everything just pops in. But how do we know if the player is falling yet? Well, we don't actually know. In fact, we can only tell that, oh, from this first frame, we can see that there's a change in the position of the arms. But is that the standing animation or the falling animation? Well, if we continue an extra frame forward, I think we can kind of tell that this should be the player falling animation. And from here, I now kind of have a bit of a problem here. I can't tell if this frame is the start frame or is it this one. Personally, like I said, my personal convention is to always do it on the first frame in which you can see the change. So this is the first frame I can see a change here, so I'm going to do it based off of this frame. So I personally will make a cut and delete, and from here I can get the number of frames. That is how I personally do this. Hopefully that will make things a little bit better for you, Bata, for when you decide to do more data collection and measurements, because what you did, I have to say that is not very good. You have, it's kind of similar to something called p-hacking, which if you're part of research, you would definitely know what that is. Now, it's not exactly p-hacking because p-hacking involves the p-value from statistics, and in this case, it's actually the gravitational acceleration of Teyvat that influenced your sample data to, yeah, just in general, it just makes your data biased. And again, data should speak for itself. So enough about that. We now know how Bata measures height and how he measures time. The question now that we need to consider is, was Bata correct? Well, what Bata ends up measuring is that the gravitational acceleration for Teyvat came out to be about 19.47 meters per second squared. Now, I have to commend Bata on this. Bata has the closest measurement to the gravitational acceleration that I have personally measured and tested. So this is most likely, this is actually the most accurate measurement of gravity I have seen from someone else. For example, in my first video on Genshin Science peer review, the sexy e-boy 69, which is just the name that they wrote on the paper. I'm pretty sure it's just to be silly. That isn't actually the player or creator's name or online name. The point is, they measured the gravitational acceleration and it was closer to 30 or something, more or less that much. And then I saw somebody who measured gravity in fact, even in the first video where they measured gravity in video, they had a completely off measurement for gravity. And then I saw somebody in one of my comments on, maybe on this video, they actually mentioned that they got around 10. Now, of course, the question that we have to ask is, how accurate is this? So, how exactly do we test the accuracy of a value? And well, it just so happens that I already come up with a method to determine how accurate a measurement of gravity is. If you're interested on the big gory details of that, I highly recommend that you watch my video using statistics to accurately measure gravity in Genshin Impact. I really do like that video. It's one of my favorite videos that I've made. The way I actually did it is by making use of something called the R² value and of course the t-test. Now, I don't want to go into all of that detail again, because honestly I explained it better in this video, but I guess I might as well explain the r-squared value because that one is relatively quick to do. Before we can do that, we also have to understand something. When you use the r-squared value, it's sort of a measure of accuracy, but not exactly in the sense that you might think. So basically, you'll have some data, but then you also have a model. And the model's job is to predict what the data should be based on its inputs. From here, we can already see that based on this, that there is some relationship between this input and this output. Now, what the model is supposed to do is to try to figure out what that relationship is. So when you put your input data into this model, you should expect to have a predicted output. Now, ideally, this predicted output should roughly match what the output data should be. Now, it won't be 100% accurate because, well, various reasons. There could be many reasons why it doesn't match exactly, even if that is the correct model. But the point is, you can actually compare your output data and your predicted output. And how well this predicted output matches your output data is measured through the r-squared value. Now, the r-squared value can range from 0 to 1, or from 0% to 100%. And the more closer it is to 1, the more it matches data. Now again, I'm being careful with my words, not just saying accurate. Accuracy depends on if your actual data is, well, accurate in the first place and not influenced by errors that much. In any case, so essentially, yeah, we now have to figure, let me now actually show you how I would calculate the r-squared value, because, well, I mean, then again, I've actually already shown, you know what, I'll just write out all the equations again. So we have this. So I'm just going to be implementing these formulas, and then we can calculate r-squared. So we have our time in seconds and our height in meters. I'm just gonna copy that and paste it like so. So these are all the values, and if you want, we can already plot the data. Like so, and there you go. Now we have our height versus time. Our model is basically, well, this equation, but we're going to say that our predicted height, y, which I'm going to label as y, I hat, with this hat over it, that is actually going to be equal to g, I'm going to put g Bata because that is the value we use, times the time squared, divided by 2. So yeah, this is our equation, so for our prediction. And let me just write out this value. So g for Bata in meters per second squared, that was 19.47. So next I'm going to do is predicted height. I'm going to actually just call this height for Bata, that way we know what's what. So essentially we need to encode this equation. So what I'm going to do is just do this array formula. Take this, lock it in place, multiply that by this, we have to square it, and then divide it by 2. And there we go. Now we already have everything calculated as such. So that was all done. So now we have our height, our predicted heights, and now we need to do is to calculate our r-squared value. We need to calculate the SSE and SST. So SSE. So SSE, let me check the formula. It is this one at the bottom here. So there's this, that. So our yi, that is actually just simply our height here. So let me do some, this is sum of squares of our height here. So that. Then we need to subtract by 2 times some product of this that and our second array, which is this. And then we need to add another sum of squares, which will specifically be the height of Bata. Now, the next one that we need to do is to calculate SST. So let me take a look at the equation again. It is this. So it's a sum of square, then multiplied by the sample count and whatnot. So let me go ahead and make some space for now. Let's move that. And we're gonna put n as our sample count, and all we gotta do is count this. Is that correct? Let me check if that's how it, let me just double check something here. Did I measure the sample count here? Huh, I only have 43. Interesting. Okay, so I think I get what I did is I probably got rid of those 2 values that I didn't yeah, so I'll get rid of them as well. So I'm gonna move this up. So yeah, as you can see here, okay, we got some errors now. There we go. So that is our sample count. So now what we got to do is do a sum of squares. And we do that on our value for y. Then let me check the formula. Minus n times the average squared. So minus, we take n multiplied by the average of, the average of this, and we square that. And there we go. We now have our value for SSE and SST. So lastly, our r squared, it should be just 1 minus the 2. So if I take this equal to 1 minus that value divided by that, as you can see, we get an r squared value of 98.65%. Now, I would actually like to be able to visualize this. So on our plot here, what I'm going to do is change this to a line graph. Now this might look really weird at first, but trust me, I'll figure it. I'll get to it. And what I'm going to do is add another range here. C1 to this. Then I'm going to put a height for Bata into the plot. Now, again, this looks really weird, but what we can do is to fix that by going to this and changing our line thickness to 0, but now we can't see the data. So what I'm going to do is change the point size to 7. So now we have a bunch of data points, and we are able to see how the graph of Bata's gravitational acceleration. As you can see, it matches it pretty well. In fact, it matches it to 98.65%. And like I said, this is the best value I've actually seen anybody measured. However, there is a value that predicts it a lot better. And unfortunately for Bata, I did have a thing where I consider the p-value and whatnot. But basically, if you're trying to figure out if there's a statistically significant difference between this 19.47 and the best value I've measured, which is 20.4, what we have to do is use something called a t-test. And in this t-test, it outputs a probability called the p-value. Now, this p-value, depending on your level of significance, can determine if it's a statistically significant difference or not. Personally, I used a level of significance of 1%. So, if the p-value is less than 1%, then there is a statistically significant difference between 19.47 and 20.4. So, if I change this value here from 20.85 to 19.47, we can see the p-value is 0. Hold on, that doesn't sound right. There should be at least some value. Oh, so it's like 0. This isn't, wait, holy crap, this is even in percentage. 0.0000000. I don't even know how many zeros there is. So, yeah, if you're if you have a level of, if you chose a level of significance that's 0.00000000091%, then yeah, I would have some questions for you, because what the heck is that level of significance? Because usually a level of significance is around like 5% by standard, which whatever, that's just standard. It doesn't really mean anything. In my case, I chose 1% for reasons I explained in my video, but the point is, that is a very, very, very small p-value. In fact, just so you know, for those who are interested, the maximum or the range of values that the gravitational acceleration should be in order for it to not be statistically significantly different from 20.4 is that it must be within this range here. Now, exactly how do I calculate this? I will explain in a different video. Because this involves something called confidence intervals, and I'm specifically using a 99% confidence interval. Again, that just sounds like it's a bunch of jargon at the moment, but I will explain it in another video. The point is that we have this range of values, and if it's outside of that value, the range of values, then it's considered statistically significantly different. So, as you can see, 19.47 is clearly outside of these bounds, so in my personal opinion, there is a statistically significant difference between 20.4 and 19.47. So how accurate? So I guess to answer this, how accurate is this? Well, it's more or less approximately 98% accurate to the data. However, it is significantly different from my value of 20.4 by quite a large margin. And, well, yeah. If anything, it still matches the data quite accurately. Compared to others, yeah, that is a very good fit of the data. And again, if you have not seen Bata's video, I highly recommend that you watch it. I will have the video linked in the description, and well, yeah. This is pretty much where the first part of this video will end. And then for the second part, I will talk about the measurement of Dragonspine's height. That's pretty much all there is to this video. It's a bunch of statistics talk at the end, but that's how we test values and whatnot. We have to use statistical analysis to do our testing and to help us interpret data. And well, yeah, I hope you guys are looking forward to part 2, so be sure to subscribe so that you don't miss out on that. Become a channel member so that way you can actually, get access to some of the perks shown on screen. And well, yeah, that's really about it for now. So thanks for watching and hope you've enjoyed.